Assalamu alaikum and hello everyone. I welcome you all in today's webinar. It is my pleasure to introduce our distinguished resource person, Dr. Asfandyar Ahmed. He holds a PhD in civil structural engineering from University of Houston, and he is currently serving as the head of civil engineering department at City University Peshawar. His extensive research in the field of civil engineering has been widely recognized and published in several reputable journals. Today, Dr. Asfandyar Ahmed will be sharing his expertise on next generation performance based seismic assessment of structures, a topic that is essential for the safety and sustainability of our built environment. Without further ado, I would like to invite Dr. Asfandyar Ahmed to start his webinar. Thank you so much.
Thank you very much, Dr. Wakas. Assalamu alaikum, everyone. And I would like to welcome you all in this webinar. So today's topic is the next generation performance-based seismic assessment. And I would like to start with some background. The code procedure, what is a code, a building code? Building code require buildings have complete structural systems, right? It requires systems have sufficient strength to resist the specified forces, and it limit the permissible drifts under specified forces. And lastly, it requires members and connections be detailed prescriptively, right? So the purpose of building codes is the ability to resist frequent minor earthquakes without damage. And by meaning frequent and minor earthquakes, their probability of occurrence is 100 years. Okay, the ability to resist infrequent moderate earthquakes with limited structural and non-structural damage, and the return period of that earthquake is 500 years, which is sometimes called the design earthquake. And the ability to resist worst earthquakes ever likely to occur without collapse or major life safety endangerment, and its return period is 2500 years. So the building codes give you the safety, but the performance is not guaranteed, right? And if a building is affected by an extreme event and performs poorly, there is an expectation of how the building should have performed, but no implied warranty. Secondly, the only warranty is that the engineer complied with the standard of care. For example, if he has followed some building codes, the design codes, then this is the only warranty that the structure will not fail during a certain earthquake of a specific return period. For most buildings, the demonstration that a design was performed in accordance with the building code will provide adequate proof of conformance to the standard of care. And if you look at the section 104, it says the provisions of this code are not intended to prevent or to prohibit any design or method of construction, provided that any such alternative has been approved. As an alternative design shall be approved where the other one is ASCE 41, which is about seismic rehabilitation of buildings. Now, this ASCE SEI has standardized FEMA guideline document on seismic evaluation and rehabilitation. The FEMA document 178, it is the seismic evaluation of these structures and specifically the building, and FEMA 356, it is related to the rehabilitation process. So though not directly recognized by the building codes, these standards are being used as the basis for performance-based design of new buildings and seismic retrofit. So now we are moving towards the performance-based design or assessment. That what are the performance-based design? What does performance means, right? So before going into detail, we need to understand that in the first generation was what was the performance criteria in the first generation of performance-based earthquake engineering. For example, it is a house. The nameplate is it is the Joe's house, right? And there is beer and there is food in this house, and it is fully operational. Now, what does immediate occupancy means? That it has been affected during the earthquake, but you can occupy it immediately after the earthquake, right? So operational is negligible impact on the building, right? And immediate occupancy is building is safe to occupy, but possibly not useful until cleanup and repair has occurred. So there is a chance that some non-structural components have been cracked or damaged, and you need to clean those plasters and the distempers and some sort of the items from your cupboard or your kitchen utensils that might fall. So you need to clean up all those things, right? The life safety is a bit threatening because the building is safe but possibly not afterward. So during the earthquake you will survive, but uh, you need to leave the house and you need to repair it and retrofit it. And collapse prevention is that building is on verge of collapse. The building does not fail during the earthquake, but you need to demolish it, dismantle it, and you need to reconstruct it. Okay. So these were the four performance criteria in the first generation, and the frequent event that varying between 50 and 100 years of return period. So in that period, the structure you want to adopt for the immediate occupancy, so it will be more costly as compared to the structure that you construct for the collapse prevention. Okay, because the structural detailing and the requirements will be less for this structure as compared to this one. So after that, the ATC 58 project started. And what is ATC? It is the technology council. We will discuss it in detail. And it started a 10-year program which was funded by FEMA, and its objective was develop the next generation criteria applicable to design of new buildings and upgrade of existing buildings, right? So the new performance definition required at that time, at the beginning of a new century or the new millennium, performance expressed in terms of the probability of incurring the direct economic loss, which is in terms of repair or replacement cost, the casualties, which includes the deaths and the serious injuries, and the downtime, which is loss of use. So in a recent earthquake of Turkey and Syria, you might have noticed the economic losses and the casualties and the downtime of the structure, right? So it all based on the next generation performance criteria. So the direct consideration of uncertainty in ground shaking, structural response, damage, and the consequences of damage. So you have to consider all these in your performance objectives, right? So first step is to select the performance objectives, which is to be selected by the owner, the designer, and the building officials. For instance, in Peshawar, the PDA is the building official, right? The second step is to develop the preliminary design and to check or assess the performance capability. And then, does performance meet the objectives? If yes, then you are okay. If no, then revise the design and continue this cycle until you get this yes, and then it is done. Okay, and it is done by the building official and the peer reviewers. So it was a very small introduction about today's topic. Now I would like to give you some insight about the performance based earthquake engineering. To transform earthquake engineering assessment and design, it was the traditional approach in which was non-scientifically defined seismic hazard. The indirect design approaches instead of indirect design approaches, and you define outcomes with probabilities of achieving them, right? So there are some well-defined outcomes and you have to achieve those outcomes. The FEMA 273 or 356 and AISCE 41, they gives this assessment criteria where you can see that the base shear demand and the lateral deformation are plotted, and the lateral deformation increases, causes the base shear to increase up till this peak or the ultimate strength value, right? So till this point where initially your structure acted as an elastic member, or the within its elastic range, right? So up till this point it is called the operational. After the operational, it is in the range of life safety, and till this peak point, the last maximum or the ultimate point, it is structurally stable and it will not collapse. But after this point, the structure will collapse. So you need to be careful about this peak point or the maximum resistance of the structure. The frequent earthquakes, which have the 50% probability in 50 years, it will resist those earthquakes in this elastic range. The occasional events, which has the 20% of probability in 50 years, it will occur in the within the operational range, but in the inelastic range, right? The rare events that will happen, which has a probability of 10% in 50 years, they have they will lie in this range. It means that the structure will resist those earthquakes in this range. And very rare events, which is also called as the maximum considered earthquakes, the structure will resist them at the ultimate load, but eventually it will not collapse and it will be at the verge of collapse. So the inhabitants will be safe during the earthquake. Now, yesterday means the previous performance-based earthquake engineering was this, what we just discussed in this slide, right? But it is not the today's performance-based earthquake engineering. What is today's performance-based earthquake engineering? As we discussed in the previous presentation, that it is more about some well-defined objectives, that what will be the replacement cost, what will be the casualty rate, and what will be the downtime in days, for example. So if you are talking about life safety, right? So the life safety, at the life safety, the replacement cost of the structure will be about 75% of its total cost, and the casualty rate will be 0.01%, and the downtime will be about some 50 days or 60 days. It means that you cannot use the structure for about 2 months. So this is more realistic, and this is what you can tell your customers, and you can tell the client, because it is more understandable language. So the performance based earthquake engineering is changed today, right? The damage assessment of the non-structural fragilities it is as important as the damage assessment of the structural fragilities, right? Because in the previous approach we just need to consider the structural elements, and we need to just draw their fragilities, and we have to analyze the structure. But in the next generation performance based assessment, we need to consider those non-structural elements, and we need to consider their failure pattern as well. So in this side you can see that the graph is between the inter-story drift ratio, right, and the probability of damage state. So for a given drift ratio, you can see that the replaced partition, which has severe damage to gypsum board and distortion of metal frame, its probability of damage is much less as compared to this orange one, which is about the replaced gypsum boards, right? And its probability of damage state is much less than as compared to this green one, which is about the patch, retape, and paint the small cracks only. Okay, so different non-structural components will have different fragilities, and they will have different probability of damage state, subjected to a same amount of inter-story drift, right? So we need to consider their fragilities and their failure pattern during the earthquake, because in the recent times it is becoming more and more important. And especially the earthquake happened in Italy in 2011. uh, the the airport was closed or shut down because of the failure of non-structural systems. So nowadays it has become very important to consider the non-structural elements as well. Now moving to the performance based methodology. So you have to define the intensity measure, right? The intensity measure is your time history. For example, you take the time history history of some kind of earthquake, and you model your structure and you run the time history analysis. I'm just using time history analysis for instance. You can use different methods, and from that you measure the damage that occurs in this structure, and on the basis of all these parameters you decide your variables. For example, how much was the collapse and the casualties, how much was the direct financial loss, and how much was the downtime. In performance based assessment you need the incremental dynamic analysis as well, and in the later part we will discuss that there is an alternate to this incremental dynamic analysis because it is a complicated thing, and everyone cannot perform it, and you can do it with the standard pushover curve as well, and I will show you that how you can perform the incremental dynamic analysis with the standard or static pushover analysis. Okay, so these are the ground motion records of 44 earthquakes, and they have drawn this incremental dynamic analysis curves, and this one is the mean curve, okay, which is required. So these are, as you can see, the plastic hinges. These are locating the plastic hinges. For example, the structural drift is when structural drift is 0.05, so it will show you how many plastic hinges will occur in this structure, right? And when you move beyond that point, how many plastic hinges will then further occur in this structures. And these are the the ground motion intensity points, and you have to find this mean point to draw this curve. This is mean annual frequency of collapse, which you just find from this hazard curve and the collapse CDF, right? So the collapse performance is that from this curve, the margin, as you can see that the margin, the SA, which is the spectral acceleration of collapse, is 2.7 for maximum considered earthquake, and 5% probability of collapse under design MCE, maximum considered earthquake, is equal to 5%. So we are considering this 5%, as you can see from here, which is coming from this point. This is your hazard curve, and the hazard curve is they draw it for a specific region. For example, the hazard curve for Peshawar will be different from the hazard curve for the Abbottabad. So for different regions, the hazard curve is different, and it shows you the spectral acceleration and the mean annual frequency of accidents, right? So this is your 5% probability of collapse under design maximum considered earthquake, and where it hits this log normal CDF. So it gives you 2.7 of the structural acceleration. Now mean annual frequency is taken as 1 into 10 power minus 4, which is 0.5% in 50 years, right? So which was the maximum considered earthquake. Uh, uh, the non-structural damage and losses, you can compute it by different toolbox and different methods. What are the input required? The fragility functions, the cost distribution of the non-structural elements, the table of damageable assemblies, and the structural analysis results. So all these three goes into this toolbox, and they give you the cost, the operability, the fatalities, and the downtime, right? Which we are keep on talking again and again. So the performance-based earthquake engineering methodology, the ground motion hazard characterization, where you have to define this impact measure, for example, the spectral acceleration, the selection and scaling of the ground motions. The second step is the simulation, right? Engineering demand parameter. The choice of engineering demand parameter is, for example, we talked about the drift, right? Let me take you to the graph. See, here the demand is structural response in terms of drift. Also, if we go back to here, also the demand parameter is inter-story drift ratio, right? So it depends on you what you are gonna take as the engineering demand parameter. You can take it as a drift, or you can take it as a floor acceleration, or any other. For example, the velocity, the fidelity of simulations to model the collapse, right? The third step is the damage modeling. So first you have to define intensity measure, then from intensity measure you have to define the engineering demand parameter, then from the engineering demand parameter you have to go for the damage modeling. For example, the taxonomy of the components, the definition of conditional EDP to DM, that is damage function. And the fourth one and the final one is the loss modeling, right, which is called the decision variable, DV. So definition of conditional DM, DV loss functions and the downtime and injuries fatalities are a challenge to compute exactly and accurately. So this is basically the flow chart. It goes upward. You have to define the intensity measure, which is the earthquake hazard characterization, right? You select some certain earthquake and you take it as your intensity measure. Then you find the engineering demand parameter. For example, you subject your structure to that earthquake and you simulate the system response. And due to that system response, you quantify the damage measures, which is called the damage measure, the third step. And the final step is on the basis of these damage measure, you define your decision variable, which is relating performance to risk decision making. And these are in terms of uh, the things that we just discussed. For example, the spectral acceleration can be your intensity measure, and you can use multiple SAs, epsilon, which is the strains, right? The SD, inelastic duration. The EDP, as I already discussed, can be drift ratio, floor acceleration, local indices, etc. The damage measure can be physical condition and consequences or ramifications, and the decision variable can be loss, functionality, downtime, casualties, etc. This is the equation that has been used to compute this decision variable, and it depends upon DV, DM, EDP, and IM. All of them we have just discussed in detail, right? This is an example of the simulation model that you run the simulation, you get the structural analysis result, and you uh, get the structural response, and on the basis of that you measure the damage variables. And after that I would like to take you to what is the FEMA P58. So FEMA P58, you can just simply Google it, and you can see that the history of FEMA P58, what it says that it started in 2001. You can get all the details of ATC 58, the Applied Technology Council, and they performed the research for more than 10 years. And then they have given you a complete package, right? And that complete package is about the next generation performance based seismic design guidelines, and you can follow these guidelines and you can just perform the seismic next generation performance based seismic analysis of your structure. But you need to understand what are the requirements of this system. For example, you can go to different you know the volumes. There are different volumes, volume 1 to volume 7, and you can download them, you can read them, and it will give you a very detailed description and the requirements that you need to follow in order to perform this performance based assessment, which is the state of the art method. You can download different supporting tools, right? Here you can see that you can download all the 7 volumes, and they are describing different uh, things. And for example, you the supporting electronic materials, it is given in this link. So when you click it, you will go to the window where you can download all these things, right? So it will be helpful, and you will see in the coming part that how you can use it. So FEMA P58 is a probabilistic performance prediction methodology, and it took 15 years. and it took 16 million plus dollars invested, right, on the 100 plus members on the team. So FEMA P58 is tailored for building specific analysis in contrast to most risk assessment methods, right? FEMA P58 output results are the repair cost, repair time, safety, fat and injury fatalities, and casualties. The overview is that you need to define a ground motion hazard, and you run your structure, and the structural analysis will give you the structural response. Then you need the fragilities of your structural elements and the non-structural elements. So you need to put the component damage, and on the basis of that component damage, it will give you the casualties, repair time, and economic loss. The comprehensive and credible benefits are that it took a lot of resources. Just like we discussed, the standardized and repeatable consistent FEMA P58 damage and repair cost databases are used consistently for all analysis, right? Because it is created based on 20 plus years of research, and the analysis incorporates the specific nuisance of the building rather than being based on a building class. So you can use it for a variety of buildings. The transparent and open source FEMA P58 is open to the public, just like I show you. You can go it and download it for yourself. It is open to the public, and you can see all the details of how the assessment is done, right? And these are the detailed steps of the method, and I will show you the method by following these steps. The site hazard, the structural response. I think this is fifth or sixth time that we are keep on repeating these things, because these are the fundamental steps that we need to follow. The structural component fragilities, the non-structural component fragilities. This is the new thing that you will understand in this exercise. And then FEMA P58, which is using Monte Carlo analysis engine, and it runs and it gives you the results, right? So instead of performing the things here, let me take you to that software which is called PACT. You can just download it. It is here. The first one, you can see performance assessment calculation tool, which is executable software for PACT version, which this is the latest version 3.1.2, and you can download it. It will get downloaded very easily, and just run it, and you will see interface like that, right? So here are different buttons. These are related to the your PACT operation, and these are related to your PACT utilities. For example, before going to the PACT utilities, I will take you to the how it works. For example, go to the model the building and import analysis results. So just click it, and an interface like this will open. Okay, so here the first tab is about the project information. You need to enter the information of the project. For example, the project ID, the building description, the client description, the engineer description, and the cost multipliers, right? The date cost multiplier and the region cost multiplier. For example, if it is going to happen in 2024, then the cost multiplier will be, let's suppose, 1.25 to the original one. And it also depend upon the region. You can also do it. For example, there will be cost difference in Karachi and in Quetta, right? Or a remote area, for example, in Gilgit, the cost will be much more than in the main hub, right? So you can define this basic project information. The second tab is about the building information, and you can see the different blinking icons. You need to put the values in these uh, tabs, right? You need to specify the total replacement cost. For example, this is the cost of your project. Let's suppose your project cost 10 million rupees or 15 million rupees. So you have to define this the total replacement cost, because all the costs that you will get will be in term of this total replacement cost, right? The percentage of this cost, the replacement time, which is in days. So you need to define your total replacement time, that if you remove this structure and reconstruct it, how much time will it take. The core and shell replacement, for example, if you don't need to replace the entire structure and you just need to replace the slab, for example, or some other core elements, how much time will it take? And it will be in the terms of the amount or money. Okay, the maximum workers per square feet are required. So it is per square feet, and you have to define here, because it will give you the details. uh, the most typical defaults, the floor area, it will ask you the floor area, the story height. So all the data, the regarding your building information, will go into this tab, right? And the third tab is about the population, because it is very important to know that whether it is a commercial building or a residential building. And what's the difference, let me show you. If you are designing or assessing a commercial building, so you can see that the population model for that is, let me select right. So here you can see that 12 in the night, there is a 0% of probability that someone will be in the building, right? But in the 10 a.m. In the morning, you can see 10 to 11, there is a 100% probability on the weekdays, right, that it will be fully occupied, for which it was designed originally, right? So it gives you the probability of happening that earthquake, for example, at what time of the day and what day of the week, if the earthquake is happening. So what will be the population model? And it is very important. If you check the graph for this commercial office, you can see it is like this, right? This is for the weekdays and for the weekend. Okay, let me tell you that for the weekdays, it is coming from 0 to 4, because in the peak number of occupants per 100,000 square feet is 4. You can increase it, you can make it, for example, 50, right? So it is up to you. And if you uh, go to, for example, in the weekdays, it is coming from 0 at the 6 a.m. to 50 at the 10 a.m., right? And then the break, and then again coming back from the break, and at the 7 p.m. in the evening, it is again going to 0 for the weekdays. And for the weekends, it is 0 up to 7 a.m. And there is a 5% probability, so it is most probably 2.4 persons are in the building till 6 p.m., and then it is going to 0. Now if you select residential building instead of this commercial, so what will happen, for example, it is a multi-unit residential here and here as well. So you can see that the weekend is just opposite to that of the commercial one, right? Because uh, everyone will be at home in the night, and they most probably go out in the morning, spend day outside, and then come back in the evening, right? So this is for the weekend. And for the weekdays, you can see that for the weekday, it is that its probability that in the residential units, it will be it will not be occupied. For example, in the night, it will be completely occupied, because here the units or the peak number of occupants is 3.1, so it is occupied 100%. And let me take you here, you may easily understand. So on the weekdays, it will be occupied 100% in the night, and 20% because some inhabitants might stay at the home, and they not need to go for the jobs or the business or some sort of activities outside the home. So in the weekend, the probability is that it will be at least 50% populated. So this tab will give you the population density during the week and during the day of a week. So it is very important to define it correctly. Then a very important tab which is called the component fragilities comes, and for that you need a tool which comes here, you know, provided fragility data. You have to download it, and it will give you this Excel sheet, which is this normative quantity, right? So it asks you that how many floors are in your building. So for example, you have said that there are 5 floors. Okay, so you need to add the details here. For the first floor, how much is the total area of the floor? For the second, third, fourth, and fifth, you need to define the floor area. You need to define the occupancy, that it says that these 4 floors are occupied by the laboratory, and there is nothing on the roof, right? Occupancy 2 is that on the first floor with the laboratory there is an office. On the second floor there is also an office. On the third floor there is also the retail, and on the fourth floor there is also a retail, right? But you can see that the 50% of the floor area is has been assigned to laboratory, 20% has assigned to office, and 30% has been assigned to school. Okay, so all of these sums will give you 100%, because 30 plus 20 plus 50 gives you 100%. So a complete floor area should be occupied by different occupancies, and you have to define them here. After defining this, okay, you just click this compile, and it will give you that how how many groups should be in your structure, how many structural components and how many non-structural components should be in your structure, given that you have provided these details. So this tool will help you that how many, for example, wall partition of gypsum with metal stud have to be used in the interiors, right? Similarly for floor finishes, wall finishes, the ceilings, etc. It has calculated all these things based on the details that you have provided in this highlighted area, and you can calculate it here, that what are the claddings for the gloss wall area, and what are the 10th percentile quantities, and you can name it. You can just specify it for your structure, and after doing this you can just go to your pact, and you can easily specify that, okay, for example, I am working on the floor 1, and what will be required in the foundation. Okay, so you can select in your foundation any type of fragility that has been given to you by that software. If you select it, it will give you the detail. Okay, so okay, I am not going to show here. I will open an example, and then I will show you these things. Okay, so just now we are going through it. The next step will be the performance groups, and it is linked to this component fragilities. Once you define it, then you can just export it here. You can click the update table in direction 1, direction 2, and non-directional. So you can import the data over here, and you can go to the next step, which is the collapse fragility. The collapse fragility for your different structures, you can define it. For example, the median and the dispersion, and you can define your collapse fragility for different floors as well. The next step is structural analysis, and as we discussed in the presentation, that the structural analysis is basically it requires the incremental dynamic analysis, right? But everyone cannot perform the incremental dynamic analysis. So pact or the FEMA P58, they have provided a tool which is called static pushover to incremental dynamic analysis, and when you download it, it will be in the form of this Excel worksheet, and it gives you the instructions that what you need to follow. See, it says that it was developed in January 9, 2012, and has been used since then successfully. So after reading these instructions, you just go to this first sheet, which is about SPO. So this is the place where you have to put the details of your structure. For example, the weight of this structure, you have to define the weight of your structure, you have to define the height of the structure, and you have to define its time period, right? So in this region you have to provide the pushover curve for your structure. So you just need to perform the pushover analysis, and you put the values in this table, and it will be like this. For example, this blue line, this is the pushover line, right? See, it is highlighted here. So when you will put your data, when you copy and paste your data in these cells, your pushover curve will be different than this one, right? Of course. And then you need to fix this curve with your static pushover curve, right? So these are the things, these are the inputs that you need to adjust in order to fit this dotted curve with your pushover curve, right? So you have to define the elastic point and its drift, for example the roof displacement and the base shear. So you have to define your first point, which is for example this one, which is 840 and zero point 0.7. So you can see that 840 and 0.7 is your first point. The second point is 912 and 1.3. So the second point is 912 and 1.3. Since they are overlapping, therefore it is showing you the detail for this one, 911 and 1.31, and then 0. It is coming to 0 at 1.31. See, so this curve, this dotted curve is fitting your static pushover curve, and once it fits your static pushover curve, then it is very simple to calculate this spectral acceleration, which is required to put in your packed software. For example, here you need to define the SA, which is the spectral acceleration, right? So there are different things that the assessment time should be scenario based or the intensity based. For example, if I select the intensity base, then it will say, okay, you have to define for specific earthquake, right? So it is easy for me. Also the analysis type, it says whether it is non-linear or the simplified linear one, right? You can go for whatever you have performed. And the scenario or intensity information, for example the number of demand vectors, what are your number of demand vectors, and the number of realizations, how many simulations you need to perform. Okay, so let me take you back to this SPO to IDA. So here there are three methods that are defined because select multi-degree of freedom to single degree of freedom scaling. Since your structure is a multi-degree of freedom system, but this tool, this software, the Excel sheet, it is applicable for the single degree of freedom system. So there are these three methods which you would like to adopt for transforming your this MDOF to the SDOF system. And you can see that the first one is equal to Fy divided by weight of the, which is the simplest type. Okay, simplest but may become inaccurate. The second one is use coefficient, which is from code or eigenvalue analysis. This is much more accurate. And the third one is results from response spectrum analysis. This is also a very accurate method. So if you select this first one, for example, just look at this yellow box. Okay, when I select this first one, so the value has been changed to 0.1458, which is the first method, the result of the first method, right? When I click the second one, so the value changes to 0.1903, which are results of the second method. And when I click the third one, so it changes to 0.1647, which are the results of the third method. So from here you can select your spectral acceleration, right? And you can also get your dispersion beta. And after that you can check different details, for example the incremental dynamic analysis results, the calculations, the GUI, the 16 percentile, 50 percentile, and 84 percentile results, and much more. So whatever you want to know about your structural analysis, that how it converts your static pushover to incremental dynamic analysis, and then your multi-degree of freedom system has been converted to single degree of freedom system, you can check this file in detail. Okay, so once you get the things from that, you can just put it here, and it is not clear to me due to the header bar. So okay, after structural analysis, you have to define the residual drift, and then you have to define the hazard curve. So without wasting the time, let me take you, let's open an example, a solved example. For example, I have done a 3-story confined masonry, right, back in 2018, and let me open it for you. I think we are also running out of time because it was supposed to be of 1 hour. And from the start, let me take you from the start. You can see the details that I have provided, the details whichever suits to be provided, the total replacement cost, the core and shell replacement cost, the replacement time, the maximum workers, the story details. You can see the floor area, the story height, all the details are provided here, right? Then for the population, I have selected the multi-unit residential, and I have explained it to you. The component fragilities, just like I show you this tool, that I use this tool to get the component fragilities, that which components will suit my structure, and then I selected them. You can see here that it is for the floor 1, then you can move it to floor 2, you can move it to floor 3, and then you can move it to floor 4, right? So all the floors will have different requirements depending upon what you have defined. Then going to the performance groups, see these are the performance groups in the direction 1. Then when I select direction 2, so these are the performance groups in the direction 2, and when I select the non-directional, so it changes, right? And it was for the floor 1. Now go to the floor 2, floor 3, and floor 4. So at the 4th floor, there are no directional components, no direction 1, no direction 2, right? So on floor 3, it is, I think, more or less like the previous floors. After that, you have to define the collapse fragility. For example, for floor 1, floor 2, floor 3, the mode 1 will cover, it comes from my non-linear time history analysis, and the mode shapes that I got it from there. And these are the collapse consequences, that what will be the fatality rate, the mean value of fatality rate, and the fatality rate coefficient of variance, the injury rate mean, and the injury rate coefficient of variance, right? So you need to define these things. So here the median is 3.35 and dispersion is 0.63. And then the structural analysis, which I got from the tool that I just showed to you, which is SPO to IDA, and the results from this point, right, are used here. For example, the spectral acceleration that has been provided to me by that tool, I have used over here, and I have used 8 intensity parameters. For example, intensity 1, intensity 2, it gives me a different value. Intensity 3, so you can see that the acceleration value has been changing, right? Intensity 4, intensity 5, 6, 7, and 8, right? So for all 8 different intensity levels are giving me different values of this spectral acceleration. And also please keep in mind that here the direction has been selected as direction 1, and the demand type is selected as story drift ratio. You can change it to acceleration as well. Okay, you can add intensity, you can delete intensity, it is up to you. After this structural analysis, I will show you this residual drift, right? The residual drift is median with the 0 and the dispersion with the 0. The median irreparable residual story drift ratio, and the dispersion, and the hazard curve that I told you previously that it is drawn specifically for some region, for example, for Peshawar region or for Abbottabad region or for Muzaffarabad region, the hazard curve will be a unique curve, right? And after putting all these details, now what will be the next step? The next step will be that just go to that tool, the main interface, and click this evaluate performance button. And when you click it, it will ask you about which one you want to run, right? So open building project and the one we just saw. So just click this run evaluation, and it will evaluate your model and all the details that you have provided. The warnings are common until and unless you have done a blunder. It will give you, see, it gives you that the analysis has been done. So just click this examine results. So now you are going to view the results of all your analysis, the performance based results, right? So the first one tab is about the repair cost. You can see the repair cost on the vertical axis, and you can see the performance groups. For example, for the curtain walls, the uh, cost is very low, but for the partition wall it is becoming high, and for the partition wall with the wallpaper, it has become more and more, it has become higher, right? So the casualty rate is about 0.02, and the injuries are increasing, the probability of injury is increasing, and it is going to 2 with this log normal value. You can see the repair time of the structure. You can see for the floor 3, the repair time is about 2.5 days, and for floor 1, the repair time is about 4 days. And what is this red? It is showing you that it is the repair of partition wall for gypsum with metal studs, and the green is the partition wall or gypsum plus wallpaper. So it is giving you the repair time for each and every component individually, right? The unsafe placards, that the curtain walls that will uh, damage, its probability is very less as compared to the residual drift and total probability. Also the realizations, the data drill down, and other details. There is another way you can check these results. For example, show time based results. When you click this button, it gives you uh, the values in this form, right? Which is time based results. You can also the loss area charts, right? For example, for the repair cost, this is your repair cost in a three-dimensional way. For example, the annual probability of accidents, the repair cost, and the intensity number, right? Similarly, this is for the repair time. This is for the fatalities. From fatalities, they mean the deaths, right? And these are the injuries. So you can check the results in this interface as well, and you can check the result in this interface as well. And you can also go for different intensity numbers. For example, for intensity number 8, the results will be totally different, right? For example, the repair cost, the casualties, see, the casualties have been changed as compared to the first one. The repair time, it is now the red has been removed or minimized for the floor 1, and there is a yellow one which is about wallpaper full height fixed below and fixed above, right? And there are other parameters that you can check for your intensity numbers. And there are some other things. For example, let me take you to this fragility specification manager, but before that, let me take you to this point where you, for example, this was a point where you can see you have to define the component fragilities, and I have selected, for example, structural steel elements, right? So what does this mean? That what will happen if I select in the roof construction the structural steel elements, okay, B103. So let me take you to show that what does it actually means. So the fragility specification manager, it will take you to all those fragilities, to all the library, and if you can see that how many fragilities they have defined. So there are thousands of fragilities for the structural and non-structural components that they have defined, and that's why they were saying that it took 20 years for them to compile this data. So B103, for example, let me take you to this steel columns, okay? For instance, what happened when I select this, and in this steel column, for example, I select this steel column base plate, right? So it will take you to the fragility definition of that steel column. This is the description, and this is the fragility curve of that steel column. The fragility curve has been drawn between the story drift ratio in radians and the probability of collapse in terms of story drift ratio, of course, okay. So the three curves shows you, the green one shows you the initiation of crack at the fusion, the yellow one shows you the propagation of brittle crack into, and the red one shows you complete fracture of the column. So at 0.1 radian of the story drift ratio, you have a less probability of complete fracture, and you have the greater probability of the initiation of crack at the fusion, right? So these are the fragility curves that have been defined into this packed software, and you can change it. For example, you can change the median and the dispersion, and what will happen, you can see the initiation of crack and the initiation of crack at the fusion. So this is your damage state 1. This is the description. This is a fraction, and this is the consequence function. For example, what will happen at the damage state 1? So the repair cost consequences, right? These are the repair cost consequences. These are the repair time consequences, and these are the other consequences. So everything for the damage state 1. Then this is the damage state 2, this is the description, and these are the consequence functions, right? The repair time, see, for damage function 1, you didn't need any repair, and this is the repair cost, and this is the general consequence information. And for the most important and the last damage state 3, right? So for the damage state 3, your repair cost consequence, your repair time consequence, and the other consequences. So you can add another damage state to these 3 fragility curves, and it will require you to define it and to add image of it, that how it will look like, and then you can save it, right? So this is how the fragilities in the pact has been defined and incorporated, and you can check them, and you can use which one better suits your results, right? So this is how you define the fragilities. And the lastly, the building population modeler that we discussed, and you can change that modeler as well for different occupancies, right? So that's all for today from my side, and if you have any question, you are more than welcome to ask.
Thank you so much, Dr. Asfandiyar sir, for such a wonderful webinar. Now, I would like to invite all the participants. If somebody has any question, please do ask the question. You can unmute yourself, or you can also type in the chat box. Yes, we will be sharing the lecture recording on YouTube. We will also provide the YouTube link later on through your email, inshallah. I think there's no question, I guess. Either the presentation was very clear, or it is too difficult for everybody to get a hold on. So, thank you so much, Dr. Esfandiar sir, for joining us in this webinar. I just want to ask you about your opinion on the recent earthquake which happened in Turkey and Syria. So how the structural engineers in Pakistan can learn something from that earthquake, and which are the specific parameters which they should be careful about?
In my opinion, first of all, I would like to tell that I am not an authority, but I am a student of structural engineering, and what I have learned from the incident that happened in recently is that we have to get ourselves update. We need to find those weak areas, because the type of construction that has been going on, it is very risky, and if any incident similar to 2005 earthquake of Kashmir happens, then I think that most of our structures will be vulnerable, and the study that I had conducted shows that we need a lot of retrofitting of those structures to be resilient. So what we need to do now is we need to work on retrofitting the old structures, the already constructed structures, and for the new construction, we should comply to the research that has been done in Pakistan, especially in terms of the confined masonry, in terms of the frame structure construction. So the URM structures that are most vulnerable to damage, and we should avoid the unreinforced masonry structures.
Thank you so much, Dr. Esfandiar. One more question on this topic specifically. What similarities do you see in the both earthquake which happened in Pakistan in 2005 and the recent earthquake in Syria and Turkey?
I think in both the earthquakes, the similarities are quite huge, because both were the shallow earthquakes, not the deep earthquakes, and the shallow earthquake also near to the population. It always release that kind of energy that most of the structures are not able to withstand that, and it happened in 2005, and it also happens again, and I think that human race is not learning from its mistakes.
So how we can play our role in this regard, especially regarding the awareness? Because
We can talk to the people, we can do webinars like this, a very a beautiful effort from coming from your side, and I think things like that, if we aware our engineering society regarding this, the designers and the constructors, those who are involved in the private construction or in the government level construction, they need to know the exact things that what need to be followed.
thank you so much, Dr. Esfandiar sir. We will be having another webinar, inshallah, soon on this topic, that what are the design parameters in which we should be careful of while constructing our buildings, and we will be conducting it in Urdu and in a very simple way, so that all the stakeholders of our construction industry can understand and apply those things in the construction industry to avoid such catastrophic devastation which happened in 2005 and in other earthquakes around the world. Thank you so much, Dr. Esfandiar, for joining us today. It was a pleasure having you and listening to your webinar. Thank you so much, all the participants, for joining us in today's webinar. We will be uploading this webinar presentation on YouTube soon. Stay tuned on our LinkedIn and Facebook pages for such further informative sessions and webinars. Thank you so much.
Thank you.